A whip antenna is a flexible, single element antenna consisting of a straight, stiff wire or metallic rod. It is the most common type of monopole antenna, widely used for portable and mobile communications. If you are operating a handheld transceiver to work a LEO satellite or running a mobile setup in a vehicle, you are likely relying on a whip. A whip functions as one half of a dipole. To radiate effectively, it requires a ground plane to act as the missing second half, creating an electrical image of the antenna. On a vehicle, the metal roof or trunk acts as a highly efficient ground plane. On a handheld radio, the radio circuit board and the operator's own body serve as a makeshift, somewhat lossy ground plane. The most common electrical length for a whip is a quarter wave of the target frequency. When perfectly tuned to a quarter wave, the antenna provides a predictable radiation pattern and an impedance that matches well with standard 50 ohm transmission lines. Increasing the physical length of a whip doesn't always improve performance. Pushing a standard whip past a half wavelength without matching coils causes the main radiation lobe to point upwards into the sky, wasting RF energy instead of directing it towards the horizon. While the quarter wave is standard, a few variations exist to manage physical size constraints. Rubber duckies, extremely short, inductively loaded whips, coiled wire inside a rubber sheath. They are highly portable but sacrifice massive amounts of efficiency compared to a full quarter wave whip. 5x8 wave whips, slightly longer than a half wave, these require a matching coil at the base. They compress the radiation pattern down towards the horizon, providing excellent gain for terrestrial simplex and repeater work. Telescopic whips, adjustable elements that allow you to physically change the antenna's length to achieve resonance across multiple bands, avoiding the need for a tuner or loading coils. Advantages: simple to build, omnidirectional, they radiate equally in all horizontal directions, and physically durable. Disadvantages: poor efficiency if the ground plane is inadequate, and they can be unwieldy at lower frequencies. A true quarter lambda whip for the 80-meter band would be over 65 feet tall. Here is a monopole antenna simulator. Watch the radiation pattern, change in SWR, change in radiation type, that is low angle versus high angle, and the lobes as length is varied with respect to a wavelength.